In this video, what I'd like to do is go over theorem number 16 on page 177 of the textbook. So theorem 16 says that the eigenfunctions of a Hamiltonian H can always be written as real functions in the coordinate basis. So that seems kind of drawn out, but we'll go through it and it'll be really easy to see what we're saying. So basically what we're saying is that we have a Hamiltonian H, and we're going to apply it to some eigenfunctions, and we're going to try and see if we can write those eigenfunctions now not as complex functions, but as real functions. So if we start with the Schrodinger equation, where I can write that out as minus h bar squared over 2m plus the potential energy operating on the wave function gives me my eigenvalue of the energy times the wave function. Now I can take the complex conjugate of it, and everything is pretty much real except for the wave function. So I'm going to take the complex conjugate of the wave function, like so. Okay, so now what we want to do, before I get to any derivations, basically again what these two equations show is that I have two wave functions, psi and psi star, which are both eigenfunctions of the same eigenvalue, which just happens to be the energy E. Okay, so now what I'd like to do is to take our wave function psi n and write it down as a real part plus an imaginary part. So we're assuming the most general case of a complex function, but I can write that complex function down as a real equation, a real function, and an imaginary function. Where in this case, the imaginary part is taken care of by I. So in the end, the functions by themselves are both real. Now, if I take the complex conjugate of my wave function, I get psi r minus I psi I. And now what I can do is I can manipulate them and do something like, if I add them together, then the two imaginary pieces subtract, and I'm left with 2 times the real part of the wave function. So now I can write the real part of the wave function as a sum of psi and psi star, and then divide it by 2. I can do the same thing to isolate the imaginary wave function. So if I take psi minus psi star, I now get 2 times I times psi sub I. So subtracting them, I get rid of psi r, the real part of the wave function, and I'm left with now just the imaginary part of the wave function. So psi I is just psi minus psi star divided by 2i. Okay. So now what we can do is we can try and rewrite the Schrodinger equation we had before. So we have these two Schrodinger equations right up here, this one and this one. And now if I was to say add those two equations together, then what I would get is the Hamiltonian operator times psi n plus psi star is equal to the energy times psi plus psi star. Now, if I divide those equations by 2 on both sides, now what I have is the Hamiltonian operating on the real part of the wave function psi sub r. So that means that psi sub r is an eigenfunction in its own right with the same eigenvalue of E. Same as psi n and the same as psi star n. I could do the same thing with the imaginary. So now let me take those 2 original Hamiltonians and subtract them. And when I do that, I get the Hamiltonian operator psi n minus psi n star is equal to the energy times the difference in those wave functions. And if I divide both sides by 2i, I'm now left with the Schrödinger equation operating on the imaginary function psi sub I, which equals the total energy times that function psi sub I back again. So now what we have is psi star, psi real, psi imaginary are all eigenfunctions with the exact same eigenvalue E. So now I basically, if I want to do an experiment and test if I can get the value of E, the energy, I could solve for this to make a prediction by either using the full wave function psi n, or I could just use the real part. Or honestly, I could also use psi sub I, which is also a real function, even the real function that then is multiplied by the imaginary number to give us the complex nature of psi sub n. So I could go one step further than that, and that is to say that if I use theorem 15 from the previous video, so theorem 15 saying if I have a one-dimensional system of bound states, that those bound states, there isn't going to be any degeneracy in the energy levels of those bound states. So pretty much you're going to have one wave function for each energy level, and and any other wave function I get out of the solution for that eigenvalue problem is just going to be a phase, some number multiplied by the original wave function I started with. So that means that I could write psi sub I as just a constant, a phase factor, times the real. Since both of them give the solution of the energy E for the eigenvalue, then they should just be the same wave function, except for now I have a phase which differentiates the 2 different wave functions, psi sub r and psi sub I. Okay, so if they're related in this way, I could go back and put them back into my original wave function, psi r plus I sub I, which is just psi sub r plus I c psi sub r, which if I now factor out the psi sub r, then I get 1 plus I c, and everything in this parentheses is a constant. So I'm just going to relabel that C tilde. So that means the wave function, the original one I started the problem with trying to solve, I can rewrite as c tilde, a constant, times a real function. So in the end, I can solve this problem with a complex wave function or a real wave function. Now, it's not necessarily cheating that I'm turning a complex function into a real wave function. Instead, what I'm doing is I'm putting all of the complexity, if you want, the complex numbers into the constant. So now c tilde becomes the complex part, and theta r is just now a real function. But what it means realistically is that if I start with my Hamiltonian times the wave function is equal to the eigenvalue energy times that wave function again, I could now put in here the real, a wave function that is a real function times a complex constant, and it is a constant, so I can pull it out in front of my Hamiltonian. And then cancel the constant on both sides, and what I'm left with is the Hamiltonian operating on the wave function, the real wave function, the wave function that is a real function. So in the end, that's what Theorem 16 gives us, is that in this particular case, we can either solve for psi n, which we know is just a complex function, or we could try and take all the complex numbers out and put it into a constant, and then solve it in terms of a real function. I mean, the good news is that the good news about writing this psi sub r, which is real, is that it also means that it's Hermitian. So then we can take advantage of any kind of linear algebra of Hermitian functions instead of having to necessarily chug through all of the math. Okay. So this is just kind of an interesting result that happens in this particular, for this particular Hamiltonian, let's say.